We live. All right. So yesterday we talked about each of you had a different area. So we drew some models, right? And we did the 100, we did a 10 by 10, right? A square. We did this one. So we did an 8 by 8. I think we did like a 16 by 4. We had a okay. We filled in our table values. We graphed. What did you find out when you graphed these yesterday? What was the shape of the graph? Stephen. Yeah, it was a curve. Kind of looks like. Look familiar? Yep. Yes. Hopefully. All right. And then these were. Let's see here. I think those were the only ones that worked out nice, right? Everything else was a little. All the other tables were just a little. The table values were a little. Oop, 21.3. We had 12.8. And we use these tables to help graph our line. So again, as our length here, as our length increased, what happened to our width? So as we increase the length, what happened to our width? What do you see the line do? Huh? Decrease. It goes down, right? And these points get smaller. Okay. So today our job is to try to find out the equation. Okay. So we kind of drew some pictures to kind of get some ideas of the different sizes, and all those they all end up having the same area, right? We filled in some table values so we could graph it. So I want you to try to use these table values and maybe kind of think about the process you did about how you found these numbers or what these two numbers equal. And you're going to try to find an equation. I'm going to give you a hint. You can write the same equation three ways. So there's three possibilities you can write. They all do the same thing. Okay? So in your group, I want you guys to try to brainstorm, and a few of you started to get some down yesterday, but I want you to try to brainstorm with your specific area what your equation of your graph, what your table will be. Okay? And again, there's three possibilities that they all, if we use those numbers from the table, they all plug in to get the same values. All right, so I'm going to let you guys work for a little while. Say about 15 minutes. I'm going to come around and just see how you can come up with the equation. Think about maybe even the area, the equation for area could help you maybe with this as well. All right, so you guys are going to really work hard together to see if you can come up with those three equations. And then we're going to come together and talk about it. All right? All right, let's see what you come up with. All right. So lots of interesting conversations with finding out the equations. So we talked to you about using your table to see if we can find the equations. What was one of the equations that you guys came up with? Now we're going to have to use this for 64 because the example up here is 64. So take what you learned with your data and help apply it to what's up here on the screen.
Would y equals 64 over x?
Okay, so you had y equals 64 over x, which meant to find the width, you would take 64 and divide it by the length, right? Now, does that work for everyone? Well, 64 divided by 1 is 64, right? 64 divided by 2 is 32. So if you plug all these values in, you'll see that it works for everyone. So yes, that was one of the equations. This one is how you could find the width. What was another one you came up with? What was another equation you came up with? Because remember, we said there were three. There were three. Angelina. Okay, so you had x times y equals 64. Okay, which basically you basically find the area here, right? So I can multiply length times width in each one, and every single time I multiply these two together, these two pairs, here, 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 I get the same number every single time, right? Okay. What was our third option? Jamie.
You say 42 over L equals W times L equals area.
Okay, so up here, L was X, right? So now we can say, well, that was this one here, the length. X was the length. So if we did 42 divided by your length, what else can we do?
Um, well, we got width. That then we multiplied it by L again, and we got area.
Right, so if you do 42, or this is your area divided by the length to give you the width. What's the other way we could write this part?
Um,
If we're finding the width, we could also find the,
we could okay, so for that one we could do x equals 64 over W.
right, and W was Y, right? So this takes, you're finding the width, you're finding the length, and you take 64, your area, divided by the width, okay? So when I take 64 divided by 64, that's 1. 64 divided by 32 is 2. So again, that's another way we can do it, just another different way of looking at it. And all three of these equations, so this finds the length, all three of these equations really serve the same function. They're just inverses of each other. I could take this equation and use our, remember how we've been solving equations all week? If I took x times y and equals 64 and I want to solve for y, divide both sides by x. Look what happens. So isn't that the same equation? I could also do divide by y and get solve for x. So that's why these are all the same thing. These are all inverses of each other. All right. Just like this, I could multiply x to both sides and go back with what I originally came up with. So they're all the same equation, just using different methods to find the same answer. Finding lengths, finding widths, finding the area. All right. All right, so let's go to our summary page. Okay, our summary page, what are some similarities and differences in the equations? So look at the equations you came up with. Look at the equations I came up with. What were some similarities?
Both of them had some sort of division.
Okay, they had a division like, y equals 64x, which basically meant your y equals your area over your x value, or length equals area over your width, however you wrote it. So they had some sort of division in it. Good. What else? What else was similar?
They both had an x and a y.
They both have an x and a y. Okay. So those equations both had x's and y's. Or we could say two variables, right? We had two variables, right? We had length and we had width. And the thing that was constant all the time was area.
Differences.
Okay, the big differences obviously were the different areas, right? Because every single table, including my example up here, had a different area, right? So even though the equations were the same, the area, these top numbers, or if you did x times y equals 64, so these numbers here were different, right? Those numbers were different. What about the graphs? I know I didn't graph mine, but if I go back over here, because I kind of quickly just sketched it. But if I think about it and I graph 164, let's say that's up here. So 2 and 32 is maybe halfway down, right? What do you notice that's similar about the graphs? My graph to your graph. Stephen.
Lots of similarities.
They have a curve. Okay, yep, they have a curve like, try to line this up as best I could. Okay, they have a curve. What else? Is this curve linear? No, so it's a nonlinear curve. All right. And if you notice, some graphs, depending on your numbers, may just be a little steeper than others, right? Because obviously, the higher the area. I think some of you guys with the lower numbers, your graph may kind of come in more like this. Because for mine, there's a lot of a decrease here, right? Where's the group that had 20? Who had the area 20? Right, look at what was your table. You start at 20, you go on a 10, 6.6, 5. So there's not a huge decrease like there are if they're the bigger areas, right? So sometimes the curves may look a little different. All right. What about the tables? What are some similarities in the tables? So if you look at my table here to your table,
None of them have a constant rate of change.
excellent. None of them have a constant rate of change, right? That's similarity. What else? What's an obvious one? Here, I'll even do this to help you. What's an obvious one?
The length.
Yeah, everyone had the same lengths, right? 1, 2, 3, 4, 5, 6, 7, 8, right? But where obviously there's a major difference is our widths, right? And the reason our widths are different is because we had different areas. All right, so let's talk about the summary part of it. All right, so when the product of two variables, what does the word product mean? When the product of two variables, answer for what? Multiplication, right? So that means when we multiply two variables, so when the product of two variables is a fixed number, also called a constant, right? And the reason it's called a constant is because that number doesn't change. Every time you multiplied a length times a width, you got that same area that you had for on your sheet, right? That number never changed. So if you had 48, that number never changed, right? That's the constant. All right. What pattern do you see in the variables? Well, depending on if you used x or y or area or length, right? You always had in this one, you had an area equal area divided by your length equals the width. You had an area divided by the width equals the length. We use the same variables, right? Those three variables never changed. How we displayed them changed, right? But those three variables never changed. What were some patterns you saw in the graph? And if you had, if you saw like any other table stuff, you saw graphs should be fairly similar, right? What can you tell me about the graphs? If you looked at my graph, you compared it to your graph. What are some of the things we talked about, Jamie? Yeah, the graphs are decreasing, right? Those y values decrease, so it's decreasing. Remember one of the things I told you when you first started to do this yesterday was take a look at the graph that you're going to draw today and compare it to the one you previously did. What were the two major differences there? What was the graph that we did in 1.1? The cups. It was linear, right? Is this linear? No, so this is a nonlinear curve. Nonlinear means it's not straight, right? So this is a nonlinear curve. And then Jamie said one, as length increased, width decreased. What pattern do you see in the equation? We kind of talked about the variables up here, right? We all use the same variables, right? We all use the same variables, but we had different areas, right? But what other pattern do you see in the equations that we talked about, that I just talked about a second ago? Those equations are all what? What do all three of those equations have in common? Nobody? The equations are inverses of each other, right? I could take that x times y equals my area, divide both sides by x, and now I just solve for my y. That's how you could find just one of them. Or I could solve both sides and solve for x and find just one of them. So they're all inverses of each other. I could use my solving equations method of using my inverses to move things across the equal sign, and I could find different parts to that as opposed to multiplying. Right? We divided, we multiplied. So this whole thing says, and if it fits this equation, it is also called, and this was the big word, inverse variation. This is not linear. We call this an inverse variation. Okay? And there's three general forms for an inverse. Your dependent variable you could solve for. Your dependent, today, your independent variable you could solve for, and you can multiply them and get that k. And that k value means something. What does the k value mean? Huh? What's the k value? Think about what was in this value with your equations. What number was replacing k in your equations? The area, which is what? What do we call the area? It was a what? Started with a C. Constant. The number never changed, right? The area never changed in any of your tables, right? The lengths and the widths did, right? The area always stayed the same. All right? And within our problems, so if we wanted to find the length, right? The length equaled the area divided by the width. If we wanted to find the width, it was the area divided by the length, right? If we wanted to find the area, we took the length times the width, right? These are all the same with this. These are the general forms of inverse variation right here. So if I were to give you a table of values, and let's say you notice that it's not linear, start thinking to yourself, well, does x times y, every time I multiply x and y together, do I get the same number? And if you do in a table, you know that now that's an inverse variation and not an example of a linear model. All right, so with 10 minutes to go in the hour, we'll let you work on the homework for today. Page 23, 18 to 26.